Okay, let's continue talking about the quality of service components in this endless series of topics included in the Encore exam. It seems that you will have to spend several months of your life, even years, studying for this exam. But let's continue with congestion management, which is a quality of service component. With congestion management, you have a certain level of control over drop packets. Let's see this example here where we have these queues, and these queues are empty, and these are queues that are going to be used to hold packets before you send them over an interface. So in this case, this queue is empty, so this packet is going to be placed into the queue, and then later on it will be sent over an interface. The same with this packet because the queue is empty. The same with this packet because this queue is also empty. And the same happens with this packet. It is allowed into the queue because the queue is empty. But what happens if we have these queues that are full? Then there is no room to hold an incoming packet. So in this case, this incoming packet is going to be dropped. And this is going to get dropped as well. And this one. And this one. If you are not using congestion management, you have no control over these drop packets. And you may be dropping here voice over IP packets. You may be dropping here video packets. So what you want to do with congestion management is having a certain level of control and maybe drop other type of packets that you are willing to get dropped first before even thinking of dropping a voice over IP packets. Congestion management gives you that control. So we have two features for congestion management. We have weighted tail drop. With weighted tail drop, you're going to establish thresholds in a queue where no more packets of a certain type are received after the threshold is met. This means that a packet of certain type arriving after the threshold is met are going to get dropped. So let's imagine that we have here this chart where the x-axis has the queue usage. And this in the y-axis, we have the drop probability. So we have a 100% of queue usage, 100% of drop probability. With weighted tail drop, you are going to set up a threshold. Then for certain type of packets, the drop probability will be 0 as your queue usage is low, but then as your queue usage starts to grow and reaches this threshold, let's say 50%, then we are going to drop 100 of these type of packets arriving into the queue. So weighted tail drop is a little bit harsh in that sense. You are not dropping any packet when the threshold is not met, but after the threshold is met, you're going to go and drop 100% of this type of traffic. Now compare that with weighted random early detection. We are going to calculate a drop probability based on some thresholds, for instance, and then using this drop probability, we are going to drop packets arriving into the queue after a threshold is met, but we are not going to drop 100% of the packets. We are going to drop a certain amount of packets according to the probability we calculated first. So if we wanted to put that into a chart, we will say that we have here Q usage and drop probability here. And then we can set up some thresholds, usually 2. And then using this threshold, we are going to calculate a slope. Where the drop probability will grow as the Q usage grows. So for a certain type of packets, we are not going to drop anything until we reach certain point of Q usage. Then we are going to drop more and more packets as the Q usage grows. So this drop probability can grow indefinitely, or at some point it can go to 100% depending on the Cisco switch you are using weighted random early detection on. So notice the difference between these two features. With weighted trade drop, we are not dropping anything until a threshold is met, and then suddenly we are going to drop any type of this certain type of packets. Whereas in weighted random early detection, we are not dropping packets until we reach a certain point of Q usage, and then we are going to use a drop probability slope in order to calculate a growing rate of drop probability as the Q usage grows. So it is weighted tail drop is a little bit more harsh. It goes from 0 to 100% probability in just an instant. And with weighted random early detection, you are slowly increasing your drop probability as your Q usage increases. Now let's go for the first feature, which is weighted tail drop. You have 3 thresholds for Q, so you can have a Q here, and you can establish 3 thresholds. It is available for egress queuing only. Remember, in Catalyst 9000 series, this weighted tail drop happens for egress queuing. Maybe for other type of Cisco Catalyst switches, weighted tail drop is also available for ingress queues, but for Catalyst 9000, it only is available for egress. The same type of packet header per queue. So if this particular queue you are going to work with COS, that is possible. But if you had another queue here, you can choose to work with DSCCP. And you also have 3 thresholds for your DSCCP. We are going to use percentage for these thresholds. We are not going to use absolute values because your queue sizes will grow dynamically. You are not really certain of what is the queue size you are working with. There is some ways to change your queue sizes or be a little bit more aware of your queue size, but that is a little bit complex. So let's think that we are going to use only percentage here. And remember that your queue size can go over 100. It can even grow up to 400%, for instance. There are 3 programmable thresholds per queue. The default thresholds are 80, 90, and 400%. And the command for weighted trade drop is Q limit. Remember, Q limit. Now, let's do some examples for weighted tail drop. So, for instance, in this queue, this particular queue here, we have 4 examples. We're talking about the same queue. These are not different queues. These are just different examples. And these are the thresholds that we have set up. So for instance, for orange packets, we are saying that the threshold is 50%. So for instance, in this example number 1, given the queue usage has gone beyond 50%, the threshold has been met. So we are going to drop this packet. This packet is not allowed to enter this queue. In this case, in the same queue, but in another scenario, has not met the 50% of usage. So we are going to allow this orange packet to enter the queue. In this other example, the same queue in another scenario has reached 50% of usage, so we are going to drop this packet. And in this other example, this queue is actually almost full, and it has gone beyond 50% of usage, so we are going to drop this green, orange packet. Let's see another example here with the same queue. In this case, for green packets, the threshold has been set to 75%. So we're talking about the same queue with different scenarios. So in this scenario, this queue is almost full. It has gone beyond 75%. So we are going to drop this packet. In this case, the queue has not reached 75%, so we are going to allow this packet to enter the queue. In this other example, this queue has not reached 75% of usage, so we are going to allow this packet to enter the queue. In this other example, this queue is almost full, so it has gone beyond 75%. So we are going to allow this. We are going to drop. We're going to drop this packet. Let's see other examples. For instance, we're talking about the same queue here. In this case, we are going to show 4 examples. In this example number 1, we have not reached 100% yet, so we are going to allow this blue packet to enter. In this other example, we have not reached 100%, so we are going to allow this blue packet to enter. In this third example, we have not reached 100%, so we are going to allow this blue packet to enter, and so on. Notice that, remember that your queues can grow larger than 100%, so at some point, if your queue has grown into a 200% size and its usage is now we're 120%, then if a blue packet wanted to enter, this queue has gone beyond the 100% percentage of usage, so it will get dropped. Okay, let's go to the next feature, which is weighted random early detection. As the same as weighted tail drop, you can have one queue using DSCCP thresholds and another queue using cost values for your thresholds. But you cannot combine them. If you are going to use this queue with DSCCP, so be it, but you cannot use cost. And if this queue is going to be using cost threshold, you cannot combine DSCCP thresholds within the same queue. Now notice here that if your Catalyst 9000 series has an UADP of 2, version 2, you only have up to 4 queues for weighted random early detections. Whereas if your Catalyst 9000 is using UADP 3.0, you can use all your 8 egress queues for weighted random early detection. weighted random early detection is not supported for priority queues, and it will use ranges to establish queues labels. You can have up to 3 ranges. That means 3 pairs. This means that you can set up 3 pairs of thresholds per queue. Now, just a note here, for all switches, there is an old way to calculate this slope. Notice that this line has a slope, which is with this slope marks the drop probability, and you will have to supply 3 values for this slope calculation. The minimum threshold will be your first input, your maximum threshold will be your second input, and your mark probability will be your third input. With these 3 points, you can calculate this slope. And then for a certain type of packets where the queue usage is low, they are not going to be dropped. But after reaching the minimum threshold, certain type of packets will start getting dropped, and this drop probability will grow as your queue usage grows until you reach a maximum threshold, and then you will go to 100% of drop probability. That will happen with the old calculation. Now, for the new calculation in Catalyst 9000, we are going to use something that is known as approximate for drop. So you're going to provide a low threshold and a high threshold, and you are going to calculate the mean value. So the weight will be the mean value. So for instance, if your low threshold is 20 and your high threshold will be 30, you will calculate the mean value, that will be 25. And then your drop probability will be 1 over this weight. So in this case, it will be something like 0.04 as a drop probability. That will be this will be the slope for your drop probability. So as the queue size starts to grow, in this case it grows from right to left, we are not going to drop any packet roll. So, and when we reach the mean value calculated from these 2 thresholds, we are going to start dropping more and more packets of this type of traffic. So this will be the slope for your drop probability. It will grow as the queue usage grows. You're going to drop more and more packets. It is not as harsh as weighted trail drop, because with weighted trail drop, when you reach a certain threshold, it will go instantly to 100% of drop probability of dropping packets. Here, the drop probability grows steadily as your queue usage grows. So let's, what happens if you have a queue? You can have weighted trail drop and you can have weighted random early detection at the same time. Notice that weighted trail drop is enabled by default, whereas weighted random early detection is not enabled by default. If you enable both, then weighted random detection, early detection will get executed first. We have this example here. We have several classes. Remember that you will get assigned 1 queue per class. So in this case, you have this class here. So you will get assigned this queue, this egress queue, and then you are setting up that you have a weighted trail drop of 80% for all the packets that happens to have a DSCCP value of 1, and then a threshold of 90% for all the packets that wants to arrive into this queue that happens to have a DSCCP value of 2, and then 100% for all the packets that wants to enter this queue that happens to have a DSCCP value of 3. And then for this other class, this class will get assigned a queue. And then for this queue, you're setting that for a threshold of 20% will be applied to all the packets that arrive with a DSCCP value of 4, and also 20% for packets that arrive with a DSCCP value of 6, and then 30% for all the packets that arrive with a DSCCP value of 5. So taking this queue, for example, when we reach 20% of usage, and then a packet having a DSCCP value of 4, it is going to be dropped. We will have a drop. It will have a drop probability of 100% once the queue usage reaches 20% for all the DSC packets that arrive with a DSCCP value of 4, for instance. And for the DSC packets that arrive into this queue with a DSCCP value of 5, something similar will happen, but they will have a drop probability of they will start getting drop when the queue usage reaches 30%. Okay, let's go to the next example. We only have this class here, so we are talking about one queue. So this queue will get assigned to this class. And we are going to set up our weighted till drop thresholds because we are using the QLimit command. Remember, QLimit for weighted drop. And then we are going to set up a threshold of 80% for all the packets that happens to have a DSCCP value of AF 13 or a class selector of 1. And then we are going to set up a threshold of 90% for all the packets that wants to arrive into our queue that happens to have a DSCCP marking of AF12. And then for our threshold of 100%, that will happen for all the packets arriving with a marking of AF11. So in this case, we are abiding by the rule of the DSCCP marking that says that AF13 has a higher drop probability than AF12, and AF12 has a higher drop probability than AF11. So this is the way to establish the standard, because we will follow the standard, and this is a way to accomplish it with weighted till drop. Okay, in this case we're setting up weighted random early detection because we're going to use the command random detect. Remember, weighted till drop with QLimit, weighted random early detection with random detect. In this case, we are setting up this queue and we are going to work with DSCCP values. And then we are setting up this 60% minimum threshold and lower threshold and 80% of a higher threshold. Remember that the queue is growing, in this case, from right, left. So this threshold apply for the DSCCP value of 10. packets arriving with the DCP value of 10 will get applied these two thresholds. Remember that we are going to calculate a weight that will be the mean value, that will be 70, and then the drop probability will be 1 over 70. And then for this other class, we are going to set up another queue, but this queue will be cost based. So we are going to use cost for this queue. In this case, we're setting up 60 and 80 for all the packets that arrive here, all the frames that arrive here, having a cost value of 1. So for all these packets, the weight will be 1 over, will be 70, sorry, and the drop probability will be 1 over 70. That will be the slope for the drop probability. Let's go to another example here. We are going to have one queue here. We have one class here, so we are going to have one queue here. And then we are going to have 3 ranges. Remember that you can have up to 3 ranges per class. We are using the 3 pairs of thresholds for this class. So for cost value of 1, we are going to set up %10 and 20. 10 and 20 for all the frames that wants to arrive into this queue having a cost value of 1. Then for the weight will be 15, and the drop probability will be 1 over 15. And then for packets that happen to have the cost value of 2 that wants to arrive into this queue, we are going to set up a threshold of 30% and 40%. That for all the packets that wants to arrive with a cost value of 2. So this will have a weight of 35 and a drop probability of 1 over 35. And then for the packets that wants to arrive into this queue that happen to have the cost value of 3, we are going to set up a threshold of 50% and 60% for all the packets that frames that happens to have a cost value of 3. For the weight will be 55, which is the mean value of 50 and 60, and the drop probability will be 1 over 55. Okay, now let's go for that will be all. As a plus, I wanted to show how to do this with all switches. So for all switches, for instance, the 3750, we have weighted drop allowed on ingress and egress. Remember that for Catalyst 9000, weighted tail drop is only available for egress. But for these all switches that are based on SRR, you have weighted tail drop for ingress and egress. So this will be the command, for instance, in order to map a queue to a threshold, to a cost value, queue, threshold, and cost value, queue, threshold, and cost value. Notice that this will be for ingress queues. Remember that in all switches you usually have 2 ingress queues and you usually have 4 egress queues. So in this case, for the egress queues, we would use output, and this will be mapping the queue, the threshold, and the DSCP value. Queue, threshold, and DSCP value. Queue, threshold, and DSCP values. Or you can go for cost map for egress, where you will map the queue, the threshold, and the cost value. 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 The queue, threshold, and the cost value. In this example, I'm not showing what the thresholds are, but there is usually a command like SRRQ threshold, and then the number of the threshold, for instance 1, and you are going to set it up to some value, for instance 50 to 100%. So there is another command that is not shown here where you will establish the thresholds. This example only shows you how to map a DSCP value to a threshold to a queue. So let's go for the other type of switches. For instance, for 3550s, we are not using SRR, but these are a little bit older because we are using weighted round robin. So in this case, I am showing how to configure weighted random early detection using WRR. This will be the commands, and that's it.